Today, we'll begin by exploring the concept of cardinality within set theory, a fundamental aspect that helps us understand the size of a set. Now, cardinality might sound technical, but it's essentially a way to answer the question, how many, when it comes to elements in a set. It gives us a measure of the set size. As we dive deeper, remember that this is not just about the number of elements, but about understanding the structure and relationship within a set. This foundational knowledge is crucial as we proceed. Let's start by grounding our discussion in the basic set theory. A set is essentially a collection of distinct objects. We consider a single entity. Think of it like a basket holding various fruits. Each fruit is unique, but together they form a collection. The elements or the objects within a set are what make it interesting. In our example, we have a set ABC. Its letter A, B, and C is an individual element. Our goal is to move beyond just recognizing what's in the set to understand how many elements it contains. This is where the idea of cardinality comes into play, which we will explore next. Does anyone have a quick example of a set from everyday life? Let's focus on the concept of cardinality, a fundamental idea in set theory. Cardinality simply refers to the number of elements in a set. Think of it as a way to measure the size of a set. We use the notation cardinality A to denote the set of cardinality of set A. For example, if we have a set A consisting of apple, orange, banana, the cardinality of A is 3. For finite set, the process is straightforward. Just count the elements. Remember, understanding cardinality is essential as it forms the basis for more complex discussion in set theory. This time, we try to focus on the differences between finite and infinite sets. Let's start with finite sets. These are sets where we can count all the elements and eventually the counting stops. Think about the alphabet. We all know that there are 26 letters, and once we reach Z, we're done. Now, onto infinite sets. These sets are fascinating because they go on forever. Take the set of all natural numbers. No matter how high you count, there's always another number waiting. Imagine trying to count forever. Quite the task, right? The key takeaway here is the nature of these sets. Finite sets have an end. Infinite sets don't. Well, we will explore how to compare these infinite sets on the next slide. So stay tuned. Let's delve into comparing infinite sets. So how do we compare set sizes? So we use bijection. Now, while we can count the elements in infinite sets, we have a clever way to compare their sizes using something called a bijection. A bijection is like a perfect one-to-one pairing between two sets. If you can pair every element from set A with exactly one element from set B without any leftovers, then these sets are considered to have the same size or cardinality. This concept might seem a bit abstract at first, but it's a powerful tool in understanding infinite sets. Feel free to think of it like matching dance partners at a ball. Everyone has a partner, and no one is left without partner. As we move on, we will explore more about these fascinating infinities and their surprising properties. Let's explore a truly fascinating question. Are all infinities the same size? This might sound like a puzzling idea, but it's a cornerstone of set theory. When we think of infinity, we often imagine something that just goes on and on, like the set of natural numbers. But surprisingly, there are actually different sizes of infinity. For instance, the set of all natural numbers are infinite, but so is the set of all real numbers. And as we will see later, these two infinities are not the same. It's concepts like these that challenge our intuition, reveal the depth of our mathematical thought. In our next slide, we will introduce a tool called the power set that helps us understand these different sizes of infinity even better. Let's dive into how the power set gives us insight into the surprising sizes of infinity. Let's try to focus on the power set as an essential tool in the set theory. The power set of a set A, denoted as P of A, is the collection of all possible subsets of A, including the empty set. Think of it as exploring every possible way to combine or not combine the elements of A. For instance, if set A consists of the numbers 1 and 2, the power set P of A includes the empty set, individual subset of 1 and 2, and the subset containing both elements 1, 2. In other words, if A has two elements, like in our example P of A, we'll have 4 subsets. This shows that the size of the power set, the cardinality of P of A, is greater than the size of A, cardinality of A. Now, we are going to reflect on this surprising idea, and this is something to do more on the Cantor's theorem on our next slide. Cantor's theorem is a fascinating concept in set theory. Let's break it down together. The theorem states that for any set A, the size of its power set, P of A, is strictly greater than the size of A itself. In mathematical terms, this is expressed as the cardinality of A being less than the cardinality of P of A. This idea is quite surprising because it challenges our intuitive understanding of size and infinity. Even when dealing with infinite sets, the power set is always larger. Cantor's theorem lays the foundation for understanding different sizes of infinities, a key insight into the nature of sets and infinity itself. In the next slide, we will show the proof of Cantor's theorem using a method of proof by contradiction. We'll see how this establishes the impossibility of a one-to-one correspondence between a set and its power set. Let's now try to focus on the proof of Cantor's theorem. The key idea here is to demonstrate that it's impossible to have a one-to-one correspondence between a set A and its power set P of A. We'll start by assuming the opposite of what we want to prove. Let's suppose the cardinality of A is equal to the cardinality of P of A. If this were true, there would be a function f that is surjective, meaning it covers every subset in P of A. This assumption forms the basis of our contradiction. By assuming a surjective function exists, we will uncover logical inconsistencies that prove our original statement that cardinality of A is strictly less than the cardinality of P of A. In the next part, we try to construct a diagonal set to further explore this contradiction. Are you ready? So we will now focus on the diagonal set, which is an intriguing part of Cantor's theorem proof. Imagine we have a function f that pairs its element x in set A with a subset of f of x in P of A. Now we introduce a special set which we call the diagonal set D. The magic of this set lies in its construction. It is made up of elements from A precisely that do not belong to their corresponding subsets in P of A. This means if X is an element of D, then X is not in the subset of f of X. It maps to. It's like creating a set that specifically avoid its own elements. This setup leads us to explore further in the next part of the proof, where we will see how these clever constructs bring us to a contradiction. Alright, focus into this intriguing part of Cantor's theorem. We have this special set D, which we defined as a subset of A. Since F is surjective, there must be some element in D, in a mapping to D, so we have f of D equals D. Now here's where it gets interesting. For our first case, suppose D is in capital D by our definition of D. D should not be in f of D. But since f of D equals D, this leads us to a contradiction because it implies that D is not in D. Similarly, in case 2, if D is not in D, then according to our definition, D must be in f of D. Again, since f of D equals D, we encounter another contradiction suggesting D is in D after all. Both scenarios lead us to contradiction proving that our initial assumption that f is surjective was incorrect. Therefore, no such function f can exist between A and P of A. This conclusively shows that the cardinality of A is less than that of P of A. So we have just proven that there are different sizes of infinity, and in fact, there's an infinite hierarchy of them. It is a profound idea and one of the most beautiful proofs in mathematics. So thank you for your attention, and I hope you have learned something today.